Hello students, welcome into our third lesson. In our second lesson, we learned about the definition of terms. Also, we learned about the equation of continuity, and also we solved some numerical problems on the application of equation of continuity. In this lesson, we are going to learn 1. The Bernoulli's effect, 2. The Bernoulli's equation, 3. The application on Bernoulli's principle, 4. We are going to learn about the dangers of the Bernoulli's effect, and also we are going to do some more examples on Bernoulli's effect and also equation of continuity. Welcome. What is Bernoulli's effect, or how does it state? It states that provided a fluid is non-viscous, incompressible, and its flow streamline, an increase in its velocity produces a corresponding decrease in pressure it exerts, while a decrease in its velocity produces a corresponding increase in pressure. So in simple terms, what we are trying to say is pressure and velocity are inversely proportional to one another. So when the pressure is high, it means that the pressure of the moving fluid is low, and vice versa. Thus, the higher the speed of the fluid, the lower the pressure it exerts. So it means at this particular point, the velocity is very, very high. And that means because the height is a good indication of the pressure, it means that if you can be able to say this pressure or this height is less than this, so it means that pressure is less. Then let's look at practical applications, practical examples on Bernoulli's effect. And the first one is a light paper held in front of the mouth, and air is blown horizontally over it, it will rise up. So if you blow air over this paper, it will rise up. Why? The paper will be lifted because the velocity of air above it, above this paper, which is this region, leads to a reduction in pressure. So pressure will reduce when you increase the velocity of air over this paper. The high atmospheric pressure acting from below this side, on the lower side of this paper, it will produce the lift, and therefore the paper will be lifted. That is the first practical example. The second one is when air is blown horizontally between two suspended balloons in the horizontal direction, the balloons are observed to move toward each other. If you blow air here, these balloons will move toward each other. The question is why? Some books are arranged on a table and a piece of paper placed on them. When air is blown into the channel made by these books, the pressure under the paper decreases, and the atmospheric pressure acting on top of the paper presses it down this way, so the paper will go down. Pressure reduces under the paper because the velocity of air under the paper increases. So if the pressure of air on this paper, under this paper, is increased, it means the pressure will automatically reduce. Therefore, the higher pressure above this paper will press it down. Lifting a ball using a funnel. This one is the most dramatic one, whereby you can be able to lift this ball as long as it is very light using this funnel. So it will move from here to here to the next somewhere here. But the reason is why. When air is blown as shown, the light ball, and don't forget, you are just blowing in, not out. You are blowing in. and the ball is lifted. At the narrow section of the funnel, this section here, the velocity of fluid is very high here than the wider section. Thus, we have low pressure on this section here. It means that the high pressure below the ball, or the atmospheric pressure, will lift the ball up to the neck. So it will be lifted to this side. And don't forget that you are blowing in, not blowing out. Then we have the relationship between pressure and velocity in the fluid is described mathematically by Bernoulli's equation. And the Bernoulli's equation is very important in physics and in engineering because it helps us to describe how the fluid moves. Bernoulli's equation said that for an incompressible frictionless fluid, the sum of pressure, kinetic energy per unit volume, and potential energy per unit volume is constant. So it is a kind of energy conservation equation. Consider liquid of mass m flowing through a pipe with velocity v. Also, let the pressure at a given point be P. Then, kinetic energy per unit volume will be given by kinetic energy divided by volume. And the formula for kinetic energy is a half mass times velocity squared. So we'll have this. But density is given by mass over volume. So you can be able to see this mass over volume here. So it means that the whole of this one will become the density. So it means that the kinetic energy per unit volume will be given by a half, law is the density, times velocity squared. Also, potential energy per unit volume will be potential energy divided by the volume, where we'll have mass times gravitational constant times the height, or what we call the elevation, divided by volume. So it means that already we also have mass over volume here, so that part will become the density. And according to the Bernoulli's equation, this one is the one we are talking about, the Bernoulli's equation, where in this case, P is, or this, the three of them are the pressures. And the first pressure is what we call the static pressure. And it only happens when the fluid is constant, it's not moving. Then we have the dynamic pressure, which represents fluid kinetic energy, this one, fluid kinetic energy per unit volume. Then the third one, this one, is called hydrostatic pressure, of which it is pressure exerted by fluid due to gravity. And this one is a good example of energy or conservation formula. This one is a good equation which represents the energy conservation, whereby energy cannot be destroyed. This equation is in form of energy conservation principle. Application of Bernoulli's principle. Bunsen burner. When gas is made to flow into the Bunsen burner, its velocity increases as it passes through the nozzle. This decreases the pressure above the nozzle. Because of higher atmospheric pressure outside the barrel, air is then drawn in. The air and the gas then mix as they rise up, and when ignited, a flame is produced. So the gas here get in through this point, or through this point here, and then we have air hole here, and then we have the nozzle here. One can ask, why is the gas not getting out of this hole toward this side. It only goes up. It is because at this particular point in the nozzle, you can be able to see it is the cross-section area of this nozzle is greater, or it's very small, sorry. It's very small. Therefore, it means that the velocity is very, very high. And that means you will reduce pressure at this point. So air will be drawn in from where we have high pressure to low pressure. So the air will get in and then to be ignited. The aerofoil. Example of aerofoils are aircraft wings and helicopter blades. And these structures are made in such a way that air flowing above it moves with higher speed than the air below it. So the point is, you are creating regions of low pressure and regions of high pressure. This implies that higher velocity of air above the aerofoil cause a reduction of pressure on that area compared to lower side where we have the low velocity, therefore low pressure, or therefore high pressure. So this is what we are talking about. So we have two pressure here. We have the pressure P1 and pressure P2, and as you can be able to see, because this side is longer, this one, you can be able to see this face is longer as compared to this. So it means that air has to move a little bit faster so that they meet at this particular point. And therefore means that will definitely lead to the area of low pressure, and the area of low pressure is P1, or leads to pressure 1. Then on the lower side, we will have low pressure because air is moving. We'll have high pressure because air is moving a little bit slower. And therefore, this region will create a region P2 of high pressure. The pressure P1 is thus greater than pressure P2. The pressure difference P1 minus P2 gives rise to the lift of the foil, and this pressure is what we are calling, or this is what we call the dynamic lift. The lifting force is given by F is given by P1 minus P2 times by area, where A is the area of the foil. And so this means that if pressure is given by force over area, it means that force will be given by pressure times area. Then we have the car carburetor, which also applies the Bernoulli's principle. And inside the carburetor, the air passage is partially constricted at the point where the petrol mixes with air. Air in the constriction is higher, hence its pressure is low. The atmospheric pressure being higher pushes the petrol to the constriction. And this is the car carburetor we are talking about. You can be able to see at this particular point here, the constriction, the pressure is obviously low because the air is moving at high velocity. And then you can be able to see that the air will be drawn here. Then we have the splay. When the piston is pushed forward, air is made into the barrel, and therefore this causes low pressure in the barrel. High atmospheric pressure on the surface of the liquid compels the liquid to move up the tube. The velocity of the liquid is increased as it pushes through the nozzle due to reduced cross-section area. The liquid therefore emerges as a fine spray, this one here. As you can be able to see, when you push this in, this the washer is pushed in through this part. It means that at this particular point here, the velocity would be very high, and this will create a region of low pressure. So it means that the atmospheric pressure around this region, around this barrel, will try to pull the spray, and then it will be pushed toward this side, outside side, and therefore it means that it will come as a spray. Then we have the Bernoulli's effect has some dangers, because as we have seen, is when the velocity of the moving fluid increases, it means that the pressure is low, and even the converse is true. So this is associated with the following dangers. The first danger is the blowing of roofs tops. On a windy day, roofs can be blown off, and this can be explained by the Bernoulli's principle, because the air flowing over the roof has a high velocity compared to the one inside the room. So it means that the pressure inside the house becomes great to a point of blowing the roofs off. So that one is very dangerous. Then road accidents. Small cars traveling at very high speed is likely to be dragged into a long track traveling in the opposite direction, also at high speed. So it means that accident can happen when the cars moving in opposite direction travel toward each other, because the air inside them is at high velocity. So it means that the pressure becomes obviously low, and therefore the two cars can be blown together, and that means you will have collision, and that one is very risky, because the atmospheric pressure will just compel them to hit one another, and therefore that creates what we call the accident. Let's do some extra examples. Water flows along a horizontal pipe cross-section area, 40 square centimeters. The speed of water is 4 meters per second, but it reaches 5 meters per second in a constriction in the pipe. Calculate the area of the constriction. Solution. We can use the equation of continuity here, whereby we say that the mass flux is constant, provided the assumptions are held, the assumptions we made later on. So we have the area 1 is this one here, and we say that you must convert into square meters. You can just multiply by 10 raised to power negative 4, then multiply by the speed of water on that section, and which is 4 meters per second. It should be equal to mass flux on the other side of the tube, whereby we have the area A1 times by the velocity on that section. So it means that A2 will be equal to, if you divide through by 5, it means that the velocity or the area A2 will be equal to 3.0 times 10 raised power negative 3 square meters. Then we have another example. Water flows steadily along a horizontal pipe at a volume rate of 8 times 10 raised power negative 3 cubic meters per second. If the area of cross-section of the pipe is 20 square centimeters. A, calculate the velocity of the fluid. How do you go about this? Already we are given the volume rate or the volume flux, which is this one, and the volume flux is given by cross-section area times the velocity of the moving fluid. So it means that The volume flux will be given by, you convert this one into square meters. If you multiply by times 10 raised to power negative 4, or you can even divide by 10,000, there's no problem. So if you divide by that, you will get this value now. So it means that the velocity of this fluid at this section is 4 meters per second. Then part B, find the total pressure in the pipe if the static pressure in the horizontal pipe is this. This is given already. Assuming that water is incompressible, non-viscous, and its density is times 10 raised power 3 kg per cubic meter. According to the Bernoulli's equation, the total pressure is given by this. Because the fluid is moving, we'll have this. We will not have elevation, where P is the static pressure and rho is the density of the fluid. Therefore, it means that we will add the static. We have the static pressure, which is this one, plus now the other pressure here, the dynamic pressure, which is given by this. So if you add the two, you will get 1.8 times 10 raised to power 4 pascals. How was the lesson? Hopefully you have gotten the best out of this lesson, and it is always good to go again and again and again until you get the best, because we provide the best. So go again through the lesson, try to grasp those points that you have not understand, and I have some good questions for you. They are here. So try to go through this assignment. They are very, very nice. They will try to gauge you how far you have understood this lesson. They are very nice ones, and the answers are still in our notes. They are there. So it's just a matter of revisiting and also discussing with your friends, and also you can also consult your teacher or call a net teacher, and we are ready and we are free every time to help you and brighten your future. And until then, let us meet later on. Thank you very much and have a blessed day.